Hello, my name is Scott Mesian, and today I'll be doing prob32 for week 7. A monatomic gas follows the process 1 to 2 and 2 to 3, shown in figure 19.32. How much heat is needed for A, process 1 to 2, and B, process 2 to 3? Alright, let's get into it. So here I have copied the little image here. First thing, you hit a roadblock right away on this problem. This problem's quite hard. You have no idea how, or at least I didn't, how, like, how much temperature has changed at point two. At least I didn't, because they didn't say, oh, this is whatever temperature isotherm. They don't say that. So you have to kind of figure it out. And of course, I was kind of stuck looking at this equation for the longest time. Um, this equation, and I'm like, okay, well, how do I know how much the temperature's changed if I'm trying to find Q? You don't use this equation. You actually remember this other equation, PV equals nRT. Hmm. If we hold the pressure constant, so this is constant, right? This is constant. The volume triples. It goes from 100 to 300 times 3. Then what happens to T? Oh, T must triple. So that's how you find that change in temperature that you need. Uh, yeah. And actually, that ends up, so the change in temperature actually ends up being 3T1 minus T1, right? So that ends up being 2T1. Yeah. Anyway, that's out of the way. Now we can go ahead and solve the problem, right? So another thing we need is N. We don't know what N is. How many moles are in this? So we actually will use PV equals nRT again, just solving for N. So if you solve for N, you'll get that N is equal to uh, P1, V1, and I'm using 1 in relation to this point. Um, what is it called? R over T1. And then you can substitute that in here. And then obviously for this C, we will have a constant pressure process. Um, yeah, and then also the question doesn't tell you, but you can look up in the book, the CP value is 20.8 for a monatomic gas, like the problem says. Okay, after all that, plug in everything, you'll actually get that temperature cancels out, and you'll just need the 2 basically. So that's kind of nice. Um, yeah, so you plug all that in, you get that this is equal to, I got 152 joules. There is a lot of temperature, or a lot of conversions in general, so be very careful with that. That is another hard part of this problem. So that would be the answer for A. For B, it's a very similar process. There's actually a shortcut you can use, just dividing this number by 1.67 and then inverting it will give you the answer. But we'll do it the hard way. So then in that case, we're going from 2 to 3. We still don't know why the temperature changed. Um, so again, we'll use this kind of same process. Okay, well, let's see. The P is divided by 3, right? So then that must mean that in this case, our volume would be the constant, our pressure is being cut in a third. So that means our temperature has to endure the same process. So in this case, it'd be um, T1 or T2 over a third minus T2. And that would be negative 2/3 T2. It's a little uglier, but it's manageable. And then you'd basically plug this number, or I'm sorry, you just plug this in along with the N, and then this time your, for B, your Q V and CV, so your CV would actually be, let me show you, it's 12.5. So if you plug in 12.5, and then for this, you'll have to do pressure 2, volume at 2, and then R will be the same. Plug all that in, you'll get a Q equal to, in this case, I got a value of, again, the temperature cancels out, I forgot to mention that. Um, and you'll just be left with this ratio. You'll get negative 91.6 joules, or at least that's what I got. Yeah, that's kind of the basics for that problem. Thank you.